1 minus P1 n minus x. Okay, so these quantities cancels out. And then we can write this quantity as combining everything under the exponent of x. So we have P0, 1 minus P1 over P1, 1 minus P0 to the x, and 1 minus P0 over 1 minus P1 to the n. Okay, so this is the ratio that we have to focus on. Okay, so this is basically based on just one x value. As you can see, only the sample item that we have here is x. P0 and P1 defined by the hypothesis. So we need to write the testing procedure. Okay, so we want that this ratio less than some value k to reject the null hypothesis, to reject A0. So when we define that, so let's write this ratio. Okay, so P0, 1 minus P1, P1, 1 minus P0 to the x. This part is the constant, but let's write it right now. P1 to the n. So we want that quantity to be less than k. Okay, so let's write everything again. P1, 1 minus P0, and less than k. Okay, so here you have to be careful about the value. So use this information. So P1 minus P0 is greater than P1 is greater than P0. Sorry. So then this quantity is higher, this quantity is lower, so it's greater than 0. So we will not have to change the direction. So we have k, and we have to the n. Okay, so we have x. X is important. So to make the x alone, we have to take the ln of both sides. Okay, so x times ln P0, 1 minus P1, and P1, 1 minus P0, less than, so you know, the taking logarithm is the increasing monotone increasing function, so we don't have to change anything. So we have the ln of this part, k, 1 minus P1, 1 minus P0 to the n. So this part is not that important actually, and this is now we have to focus on that part, because you know, when inside of the ln is between 0 and 1, we have a negative quantity. If it is greater than 1, so we have a positive quantity. So we have to define again, look at this one, so P1 greater than P0. So this part is the crucial part. So the quantity of P1 and P0 is very helpful to define the direction of the test. Okay, so P0 is smaller, and 1 minus P1 is smaller. Okay, and then so this part is smaller, so P1 is greater than P0, and 1 minus P0 is greater than 1 minus P1. So basically here the numerator is less than the denominator. So this quantity should be between 0 and 1, right? So then the whole, this ln thing is actually negative. Okay. Let me use the back side of this. Okay, so then if we continue with that, so then our rejection criteria should be x greater than, because this is negative, we change the direction, so this ln k 1 minus P1, 1 minus P0 to the n over the negative quantity that we have, P0, 1 minus P1, P1, 1 minus P0. Okay, so this part is actually, let's denote them by C. Okay, so this will be our rejection criteria. Then we can write our test function. So our test function can be written as phi x equals to 1 if this ratio, this ratio is less than k. So this ratio less than k means that x greater than c. Okay, and then it takes value a if x equals to value c, and 0 if x less than c. So this will be our testing procedure. Then we can define the values of c and a. So here the c is unknown and a is unknown. So this is a discrete case, we have to consider the probability of this event. So let's write the type 1 error in terms of the expected test function. Alpha is the probability of type 1 error. So we fix that. We already know the value of that one. We choose the value. It's under our control. And then it equals to this one under the null hypothesis. Okay. Let's say P0. Okay, so then write 1 times this expectation where x greater than value c plus a times probability that x equals to c plus 0 part. Okay, so you don't have to write the probability. So here for fixed alpha, so we have to go to the cumulative binomial tables. And then, if it is like 0.05, then with certain success probability P0 defined under the null hypothesis, because we are finding the type probability of type 1 error under the case that the null hypothesis is actually true. Okay, so for a given sample size and P0, we use the binomial cumulative binomial table. Okay, so go there and then find the values which is less than alpha. For, let's say, x can take several values, and then defining some c values for which x values this quantity is less than alpha. Okay, so define the value of c based on that one using the n and p0, and go to the cumulative binomial table, and for find the value of c, give some numbers to c, or you can write it as 1 minus probability that x less than or equal to c case, and then you can define the value like that, or let's say c minus 1. Okay, x less than. Okay, so define the value of c using this one, starting the value of c minus 1 from 0, 1, 2, and then try to stop where this probability is greater than specified fixed alpha level. Then how can we find the value of a after deciding c? So first of all, you have to find, in the first step, you have to find the value of c. After defining the value of c, okay, so now this is known, so the probability is known. This probability is also known. Okay, then alpha is already fixed. So try to write a alone. How can we do that? A equals to alpha minus probability that x greater than c. We already find the value of c. Alpha is known, and the probability that x equals to c. So after that, we can find the success probability of another randomized experiment with the success probability. Okay, so this will be the success probability of the other randomized experiment. Success of a randomized test. Okay, so it's different than this binomial experiment actually. Okay, so this is the way that we define our test. So now we know the value of c, we know the value of a, so our rejection region is known for a value of c, so everything is known. Then we can calculate the power of the test or probability of type 2 error, or we can calculate the also p-value. Okay, so let me go through the certain best test part. So this is the randomized test. So let's focus on, okay, so I forgot to tell you about if we have random sample case. So let's say we have not just one x value, let's say we have more than one. So let's say we have a random sample. Usually we assume that we have a random sample. It can be another sample also. So test function now defined by x tilde. Actually, this is, the vector of all x values. Okay, so it's the same actually. But now we are using the joint distribution, okay, under the null hypothesis, and under the alternative hypothesis, it's also less than k. You know the reason. And a if theta 0 over f of x vector when it equals to k, and 0 if this quantity is greater than k. Okay, so everything is the same, but we are not using just one value here. So here in the multiple, when we have a random sample case, you have to be careful that so our test will not just depend on one x, and most probably it will define on a function of x, like summation of xi or x bar or summation of ln xi type of thing. So to be able to define the critical value for that specific statistic, you have to use the distribution of that statistic. So you have to find the distribution of summation of xi or some x bar, or the distribution of maybe summation of ln xi. So you have to focus on that part. Okay, so we are using the distribution of some statistics in this case. So we will solve some questions in the most powerful test case. Okay, so let's start the case with the certain best test. So for binomial, we have, this is the actual testing procedure, but by using central limit theorem, if n times p is greater than or equal to 5, under certain conditions we can use central limit theorem, so we can get the approximate test. But this is the exact testing procedure. But if the sample size is big, it's very difficult to find the value of c using the cumulative binomial table. Okay, so a new topic is certain best test. So now we will start to derive the most powerful test, and then uniformly most powerful test, and likelihood ratio test. Certain best tests. Okay, so again here we start with a random variable, and we assume that we know the density, probability density function, or the probability mass function of that random variable. Okay, so start with the simple case. We assume that this one unknown parameter, so this is we have a one-dimensional case. So theta equals theta 0, simple hypothesis, versus in the alternative we have theta equals theta 1. Okay, so we have both simple hypotheses. So this is the simplest case that we will see, but we will start seeing the sampling testing procedure using these. Okay, so we have to define our rejection region. So our aim is that one. So reject A0 if some function of random variables is in the critical region C. Okay, so this is our critical region. So we need to define this critical region. Critical region. Okay. So start with the likelihood function. Okay, so we have L theta. So it is a function of theta given the sample values. So when we have a random sample, so this is just the multiplication of marginal distributions. Okay, so you already know that. And the definition of the probability of type 1 error, alpha. So this is under our control, so we are fixing this value. Okay, so this is the probability that reject A0 given A0 is actually true, where theta equals theta 0. Okay. In terms of x values, so we have to define the rejection region, and in terms of the sample random variables, because everything based on the sample information. So these sample random variables, in the critical region. So we are rejecting the null hypothesis under theta equals theta 0 case. So this is the definition of alpha. So using the likelihood function, okay, then the likelihood of theta 0, okay, so we are finding the sum of these events under this case for continuous case, or for discrete case, sum under the critical region. See the likelihood function. Okay, so what is the likelihood of this event? Discrete case. Okay, let me use the back side of this. Then we have another type, type of error, which is beta. Okay, so it is the probability of not reject H0 given the H1 is true, theta equals theta 1. Okay, and or we can write this as 1 minus probability that rejects H0 given theta equals theta 1. Correct decision, which is also known as the power of the test. Then we can define our probability in terms of sample random variables where the x values x1 to xn is in the critical region given theta equals theta 1. Okay, so everything will be based on the distribution of the sample, the function of sample random variables, and we have to define the critical region based on the distribution of the function of the random variables under the condition that theta equals theta 1 to be able to find beta. Okay, so then in terms of likelihood function, we can write this as 1 minus, again, get the sum of these events under the critical region. What is the likelihood of this event where theta equals theta 1? Similarly, for discrete case, for continuous case, under the critical region where theta equals to theta 1 for discrete case. Okay, then what is our procedure here? We want to minimize both errors. So let's consider the linear combination of these events. A times alpha plus B times beta. Okay, where A and B are some given constants. Okay, so our aim is to be able to minimize this error under the critical region, minimize this linear combination, and which C value gives us that one. So this is our main question here. Okay, so we try to derive. So this is how the most powerful test procedure is derived. Okay, so this is the logic behind it. So let's write it. Okay, so we try to minimize this linear combination, right? So focus on the linear combination and write it in terms of likelihood function. So we can do it for continuous case and for discrete case. In my notes I use discrete case. Okay, so it doesn't matter actually, so you can use both approach, so you will end up with the same result. Okay, so A times. Okay, so remember we defined for discrete case our likelihood under that. So we have this sum under the critical region, likelihood of for theta 0. Okay, and we have plus B, and then the procedure here is 1 minus sum under the critical region where theta equals theta 1 case. Okay, so we want to minimize these two quantities. Okay, so let's write the steps again. So we have 1 plus A times the critical region L theta 0 minus B times sum of critical region under the null hypothesis. Okay, and find the minimum value which C value minimizes this event. Okay, so then choose C such that any point, sample point x1 to xn, for which this quantity L theta 0, so this is the fixed part, focus on the middle part. So for each cases in this sum, basically has to support this one minus B times L theta 1 should be less than or equal to 0. Okay, and then if we write it in a ratio way, L theta 0 over L theta 1 less than or equal to B minus A. Then let me have a new page. Then our most powerful test, which is also known as the Pearson Lemma. We define our critical region C. So we have the sample points x1 to xn such that this ratio L theta 0 over L theta 1 less than or equal to some quantity B over A. Okay, so this will be our testing procedure, and at the end this ratio will be a function of x1 to xn, so it will be a function of sample random variables. Okay, so this is known as the Pearson Lemma. Okay, so we are defining our testing procedures based on that one. So if, let's say, A and B equals to 1, then basically we want to minimize alpha plus beta, and under that condition C will be L theta 0 over L theta 1 less than or equal to 1. There should be an equality sign. Okay, be careful about the equality sign. So if H0 is true, then this ratio, which is known as a simple likelihood ratio, L theta 0 over L theta 1 less than or equal to 1. So this is known as the simple likelihood ratio. Okay. Then we can define our best test. Usually A and B, are not equal to each other, so we are defining a B over A as some value K, like the previous case in the randomized test. Okay, then our best tests, let's define it by delta star. Okay, is reject A0 if this simple likelihood ratio less than or equal to B minus B over A, let's say some value K. And after that, basically this will be a function of sample random variables. We can define it as y. Y can be sum or x bar or any other function, or first order statistic, nth order statistic, whatever, or y greater than c case. Okay, so we ended up with y less than c or y greater than c as our critical region decision rule. Okay, and usually, as you can guess, since we are working with the likelihood function, this y will be a sufficient statistic. Okay, so L theta 0 over L theta 1. Remember, we found our sufficient statistics using the likelihood functions, and so the result of this ratio will be a function of y, which is a sufficient statistic for theta. Or it can be a function of joint sufficient statistics, basically, or let's say y1 to yk if we have more than one parameter cases, so joint sufficient statistics for, let's say, theta 1 to theta m. Okay, then this based on the Neyman's factorization theorem. You all know this procedure very well. Okay, so let's show that this testing procedure gives us the best test or the most powerful test. So how can we do that? We can compare its power with the power of the other tests. Okay, so